Hello, everybody. Welcome to our session today. We have a really great one. Um, I'm gonna give it a minute. I think people are still joining, so I'll give it until 3:02. If you need to run to the bathroom or get water, please feel free to do so, and we'll be back in 2 minutes. Otherwise, hang tight and we'll get ready soon. All right. If you're just joining us, welcome again. We're going to go ahead and get started with our bridge webinar by our MIDAS expert, Logan Julander. Today, we're going to be taking a look at the 5600W project using seismic design and pushover analysis. For anybody who is new to MIDAS, we are a subsidiary company of MIDAS IT. We develop a total solution service for bridge building, geotechnical, and mechanical engineering. And these are some of the software that you may be familiar with. For anybody who is new to using this platform, I know it just recently changed in terms of display, so I did want to go ahead and share some tools as well as layouts with you guys. At the top, you'll see whoever is presenting or speaking in that moment. You will be able to see the presentation screen right up front, and then if there's any active cameras, you'll be able to see that here. And then here on the top right, you'll see the session duration. If you're having any questions or issues with your settings, you can use these buttons to control that. Um, if you want to react either during or towards the end of the session, if you would like to get any attention from our end, if you have any questions, you can use the hand raise icon at the bottom left and click any of these buttons to, again, react to the session if you really like it, if you think something that was said was funny, or anything of the sorts. And finally, if you have any questions, you can submit them using the question box up here. All questions will be answered at the end of the session. If these buttons are not what you're looking for, you can also go to the gear icon and edit your speaker or microphone settings that way. So without further ado, I'd like to introduce our speaker today, Logan Julander, who is a structures manager at the Salt Lake office of Michael Baker International. He is an experienced he has experience in working on heavy highway and transportation projects, including accelerated bridge construction and digital delivery methods. Additionally, he has specific experience in writing and developing ABC guidelines, specifications, and standard detail manuals. He has also been part of the project teams on a variety of traditional CMGC design build, progressive design build, and digital delivery projects where he has designed and managed the design of bridges, culverts, retaining walls, and sign structures. Logan has worked on various structural studies, designs, and analysis projects involving complex bridges and design. Um, Logan, I'm going to make you the presenter now, and then we can get started.
All right. Let's see if this works. All right. Can everybody hear me and
Yes.
see my screen? Okay. Well, thank you. Thanks for an introduction. I'm excited to be talking about this project, the 5600 West project. This was an exciting project to be able to work on, and this had some really unique design elements, and I'll go through the process of how that came about. And first, as kind of an outline to my presentation, I'll give a project introduction, because there's really a lot of story of how this bridge evolved into what it was. And I'll go through the different challenges and solutions that led to the final design. Then go over the seismic design of the bridge and follow up with any questions you may have. First off, the project is located in Utah, near Salt Lake City, and the 5600 West corridor runs north and south, and the project limits were between State Route 201 on the south and Interstate I-80 on the north. And this stretch of road has some heavy truck traffic. Approximately a third of the annual average daily traffic is truck traffic. And the reason is that the major Union Pacific Railroad port and train yard is located here, and many large distribution facilities are along this route, such as Amazon and Costco. And so this is part of the inland port, and it's heavily trafficked. And up here on the right, it's kind of out of the screen, is the Salt Lake Airport. So there's a lot going through this corridor, and the project was to increase the capacity of 5600 West from one lane each direction road to having 2 lanes each direction with a center turn lane. And one of the main items in the project, this picture shows at-grade railroad crossing. There are 3 UPRR tracks that are crossed, and because of the frequency of the trains and the proximity to the yard, this intersection would get backed up, causing delays to time-sensitive trucks coming to and from the many areas, warehouses, and truck terminals. So you can see why having an at-grade crossing or grade separated crossing would be a main emphasis on this project. And I'll go through some of the project risks. First, the original scope and estimate. The solution for this grade separated crossing was a 160-foot bridge that would span the 3 existing UPRR tracks. And that was located in the general footprint of the current crossing, at-grade crossing. So this brought up a number of concerns, such as how would traffic be diverted during bridge construction. Also, that many of the utilities in this area would need to be relocated. UPRR would essentially be cut off from their property if we had, big 30-foot walls that would be around this for the embankments to this bridge. And so in order to facilitate solutions for these issues, a week-long value engineering study was performed where different solutions were investigated to address these problems and any other problems. And some of those solutions were to increase the bridge length, or to shift the alignment at the crossing west of the at-grade crossing, and also the use of EPS geofoam embankments. And I'll go over these solutions in the following slides. So, increasing the bridge length. This slide shows the UPRR right-of-way near their train yard, and that's highlighted in blue. And now having a single-span bridge shown in green there with these 30-foot tall walls would essentially cut off any access, any future access from UPRR to their property west of 5600 West over here. And UPR was vested in this project, and a solution was reached to lengthen the bridge to accommodate 2 future tracks on the south side. Also in adjusting alignment, by shifting the alignment to the west side of 5600 West, as this yellow hatched section shows, many of these utility relocations would be able to be avoided, including a 33-inch sanitary sewer line and an overhead transmission line with requires steel power pole relocation. And any utility under the embankment would need to be jack and board under the UPRR tracks and would need to have a protective casing. So this shift allowed the the avoidance of relocating all those utilities. It also allowed for bridge construction to be performed, off-site and away from the live traffic, and avoided a costly shoe fly and the time for maintaining that during construction. So also 5600 West traffic, those traveling along this during construction would not have their travel patterns interrupted, as this shift could be constructed offline. This shows the geofoam embankments. So shifting the alignment helped mitigate those utility relocations, but the tall walls with ordinary fill would induce settlement on the adjacent existing utilities. And so geofoam approaches were proposed and designed for a zero net load, and thereby eliminating the concerns for settlement on the existing utilities. And those who don't know, geofoam is essentially just engineered styrofoam. It's very lightweight. And the zero net loading on the existing soils was accomplished by excavating out some of the soil that was there and thereby replacing the heavier soils with this lighter geofoam. All right, and so the final bridge solution, what came out of that from the original scope of the 160-foot bridge, was a 460-foot span, 3-span bridge that would be able to span the existing 3 UPRR tracks, accommodate 1 future track next to those 3, and 2 future tracks on the south end of the bridge. And this just shows the typical section through the bridge, which is comprised of, the superstructure is comprised of Utah standard pre-stressed bulk T girders that were 82 inches deep, with a composite 8.5-inch deck. This shows the full section with added lanes, and the bridge even accommodated a shared use path for any pedestrians crossing in this area. This is the elevation view of the bridge that meets all the horizontal UPRR required horizontal and vertical clearance. At one point during the design, the UPRR wanted a 40-foot vertical clearance so they could get their gantry crane on the other side of the bridge. But once they saw what the price tag would be for that and all the other items that would influence, they decided that it would just be cheaper to buy another gantry crane to put on the west side of the bridge. So this rendering below kind of helps illustrate the use of the bent style or pier style abutments. So this was one thing that was unique. Driven pile deep foundations were used for this bridge, and there's still some unknowns about using driven piles through geofoam embankments. And so if we were to put the abutments in the geofoam embankments, we'd probably still have a cap and column supports that would go down to the bottom of the geofoam embankments, where piles would be drilled into the existing soils. And so instead of having those inside the geofoam embankments, those were brought out in front, and thereby we would be able to inspect those abutments. Now, I'll go into some of the seismic design considerations that and the seismic design for the bridge. It was unique with having these abutment or bent style abutments. But due to the proximity of the bridge to this West Valley fault zone, which is shown on the left, and also more specifically the Granger segment shown on the right, that fault, it was determined that a site-specific hazard analysis should be performed at this location. And another determining factor for the site-specific analysis was that the three-span bridge was a more flexible structure. And so the bridge had a longer period. And this graph shows the USGS standard response spectrum in black for both the 7 and 3% exceedance, 7% in the solid, and then the 3% in the dashed. And it also shows the probabilistic site-specific analysis that's shown in blue for the 7%, red and for the 3% exceedance. And so you can see the site-specific analysis does estimate higher spectral accelerations for the longer periods compared with the AASHTO standard. So it was good to see this, that it was good to do the site-specific hazard analysis to accommodate that probability. So as far as looking at the seismic resistances in this model, Utah uses integral abutments, when possible, because there's a lot of seismic resistance that can be utilized with passive pressure behind abutments, especially with deep girders like these, and superstructure, which would be like 7 feet plus. And so because these were bent style abutments pulled out in front of the embankments, we wouldn't be able to utilize passive pressure resistance. So the seismic model for this bridge utilizes plastic hinging in the columns and capacity protected pile caps. And so in designing the columns, we use MIDAS General Section Designer. We're able to put all the information in for the confined concrete section, the steel and elastic properties for both the steel and expected values for the concrete, and come up with a general section designer or design using MIDAS. And this shows the moment curvature analysis with the idealized plastic moment. This gave us the cracked moment of inertia for the columns, and overturning moments that were used for design. And also this, there is an export button that you can use to export plastic hinge properties for pushover analysis, and that can go directly from the general section designer into the MIDAS model that I'll be showing later. But this is a figure showing the MIDAS model that we used. To set up the model, we initially used the MIDAS wizard to help set up the basic layout of the girders and superstructure elements and the support locations. And then after that, the model was adjusted to fit the bridge conditions. And then the general section designer, those cracked moment of inertia values were used for the columns in order to get the seismic deflection. So we had both a a static model, and this was the seismic model that we used um, for getting our seismic deflections and calculating those. As far as the site-specific response spectrum, in MIDAS there this shows that we were able to put the values from the site-specific response that the geotech had performed in order to get those spectral accelerations into the model. Now this shows the columns and footings, and initially we had modeled the columns as fixed at the base, and that was the reason that we were considering a pushover analysis, is we had fixed base columns that we were getting initially deflections that were more than our capacity design was allowing. As the analysis progressed, we moved away from the pushover analysis and the fixed columns and modeled the piles and passive pressure on the sides of the footing as springs. And the column displacements were then able to meet the displacement demands without the need of using pushover analysis. And for any of you out there, I apologize for the description in the webinar, as it was described as using pushover analysis, which we did look through and check. So if any of you feel like you were cheated out there, there are other MIDAS webinars that focus solely on pushover analysis and going through that. That are great tools to use. But yeah, that we had taken out we had isolated just the one of the abutments or vents with the columns, and used the plastic hinging properties from that general section designer right into that MIDAS model. But anyway, this after going through and developing the models, this shows both the longitudinal above and the transverse below those deflections. And the deflections that we were getting with this flexible model is 8.79 inches longitudinally and 3.62 inches transversely. And because there were some differences in heights of the columns, which led to some, throughout the design, we were getting some interesting kind of racking sort of deflections and forces in the model. And so we had to do some balancing of the stiffness, had to add some piles to some of the abutments in order to avoid that sort of thing. And so those once we were able to do that, then we were able to get the the deflections for the model to be lower than the design requirements. So after that, the footings and piles were designed to resist the plastic overturning moments and those shear forces. that we had gotten out of the general section designer. So we'd applied those at the just on at the base of the columns on the footings, and analyzed those so that they would be able to resist the plastic overturning moments in the columns. And in kind of went through that quickly, but in conclusion, this solution to these different obstacles and avoiding those utility conflicts, and they were both costly and timely utility conflicts, while meeting the needs for the project, offered some unique design challenges that we needed to design for, and it was a really great project to work on. UDOT, the owner, was really great to work with, and as well as Gerhard Cole, and going through all the seismic site-specific hazard analysis. And then this really was a whole team effort in putting this together, and working through this, the challenges from, a 160-foot bridge to this 460-foot bridge with the bent style abutments. And UPRR really was vested in this design and this bridge, and so they were good to work with as well. But it really was great to work on, and I think we have a good amount of time if we have any questions.
Thank you, Logan, so much. We do have some questions. So the first one asks, what was the approximate depth of the existing soils removed to achieve the net zero loading?
I was surprised it wasn't that much. I'll have to go look, but it was I believe around like 4 or 5 feet, and possibly less to achieve that net zero loading.
Wow. Okay, the next question asks, was there a reason the model wasn't done as a single line model with representative properties of the entire structure instead of spending more time to model the entire structure as is?
Yeah, I was gonna touch on that, but it's I think with the kind of the wizard, it was actually pretty quick to be able to go in and just have the superstructure modeled in there. Because we had, considered that we could have just used a line, to model that. But I think there were also other forces on the bank caps that were used for that design. And really our static model was essentially just a copy with our seismic model. And so it wasn't a whole lot of extra effort, and it didn't take that long to run the model. It wasn't taking, like an hour. It was a pretty quick model. So it didn't, computing time, it didn't add really any additional. And I think because we had the static model as well, it didn't add a lot of time to do it that way. But yeah, I could see that as
Okay.
well.
The next question asks, did you verify the moment curvature curves obtained from the section designer of MIDAS?
Ooh, that's a good question. I believe we had we did essentially a spot check, but as far as the moment curvature, um, we did not do. We did some essentially some spot checking, but not like a full, like hand analysis of that to check against that.
Okay, and then the next question asks, were there any considerations for railway collision loads on this substructure?
We did not, and um, I think that the distances were the clearances were far enough away, but one thing that UPRR did want was in this extra section where they would have not trains, but other um, other equipment that would be working around the tracks would we put some barriers against the or up against the column to help avoid any collision because they UPRR was has seen that more often than not with having the equipment working around under the bridge. And really, because this is next to the yard, there's the trains really aren't like blowing through this section either. So that wasn't as much of a concern.
Okay, and then the next one asks, can you mention again why a pushover wasn't necessary? And then they asked, was it pinned column tops?
So the columns were well longitudinally they were essentially pinned, but no, the the columns were fixed at the top. But I think what when we modeled the footing contribution, then the um, the differential deflection, I guess the actual column deflection was less um, than with the fixed column at the when it was fixed at the base. And so the deflections were, I mean, they were close um, to our limit, but which was good. Why we did kind of a check to see that we did have the extra capacity using pushover, but that's the reasoning why um, we were able to not not need pushover with that modeling the foundation.
Okay, and then our next question asks, were standard types of approach slabs and sleeper slabs used to span the abutment bent to the embankments?
Um, yes, um, our standard approach slabs are designed for um, two span from the abutment to the. We did have a sleeper slab that the approach slabs rested on, and so um, we did use just the normal design for our approach slabs.
Okay, and then for this another question was the Was minus GTS&X used for the soil structure interaction, or what procedure was adopted for this?
Oh, minus GTS X was not used. We For the soil interaction, we essentially iterated the kind of the equivalent passive pressure that would be engaged based on the deflections. So we kind of iterated through that in order to get our equivalent springs for the passive pressure used on the sides of the footings.
Okay, and then the next question asks, was MIDAS integrated with CAD used at this on this project? And if so, what impact did this leave?
We had thought about that because one thing this was uh, this project was also a digital delivery project, which um, I didn't go into in this presentation, but the the a 3D model was used as the contract document, um, and at the time, I don't think Midas was as integrated with the CAD software. Um, and so we did not. I think we had looked into that um, and in using that, but in the end, we did not use Midas to go to CAD or vice versa, or in utilizing that.
Okay, and then next it says the outside spans seem long compared to what balanced spans would be. How did that affect the seismic forces applied to the abutments? Was there any attempt to change the layout, and if so, was that not possible?
Yes, that is a good question and a good comment because we do realize that the center span was shorter than the end spans, and that I think did make it did affect the seismic model, um, and the reasoning was to be able to get those clearances to the future um, railroad tracks, those two tracks, and also that first span had to span over the um, three existing UPRR tracks. So it kind of um, made that a little difficult to get those balanced. Um, and so there definitely was some we had to work through that, and that's where we had to balance out our um, where we had more piles and especially with the um, column height differences as well. And the another solution would have been to use a two span steel girder bridge that was that would have just one pier or bent in the center. Um, but this worked out to be um, the most cost effective solution for this project.
Okay, and then Bear with me, we still have a couple more. What factor for live load was used with the extreme event one seismic loading? And was it required by the DOT or was it defined by AASHTO?
Good question. So UDOT, they do define um, the live load to use for extreme event, and that is 25% of just the lane load, not the um, not the truck or the HL93. So that is prescribed by UDOT to use for seismic analysis.
Okay, and then the next one asks or states there is a gap between the abutment columns and embankment behind. Was it bridging this gap?
The approach slab is bridging that gap, and the gap was there to allow for that seismic movement, um, and also to be able to work behind that. But yeah, basically for that seismic movement, there's that gap behind the the back of the abutment cap and the wall.
Okay, and then we have, did you apply the collision load on the pier from the train?
Um, no, we did not. So it was outside of those clearances where that is required or where protection is required for the columns.
Okay, and then the next one asks, why did you consider the footing fixed and do not model the foundation for demand capacity calculations?
Oh, so we did shift from modeling it as fixed to um, having it on modeling it with spring supports. So we we moved past, I guess, that design in our design. So initially we had looked at it as fixed, but then moved towards the contribution from the footing. And the reasoning, I don't have the exact wording, but in the AASHTO seismic guide spec, it says, what percentage your footing contributes. You can, if it's a minimal percentage, then you can um, model it as fixed. But we ended up having a contribution from our footing, so we did model that as not as fixed.
Okay, the next question asks, have you considered running a nonlinear transient analysis to determine the structure's response?
Um, we had not, and I, as far as like, I don't, I don't think that was necessarily in scope um, to to do that, but um, we did not do that.
Okay, and then did you consider a fix at top as well as pushover analysis? Sorry, no. Did the column consider fix at top as well as pushover analysis?
Okay, in the longitudinal direction, it was not. It was um, essentially at the top of the cap, at the bottom of the girders. It was pinned, but in the um, transverse direction, it did. I mean, essentially the columns had the double curvature, so it was more fixed at the tops of the columns. And yes, we had looked at that, designed it that way.
Okay, and then the next one we have asks or it states, you mentioned spot checks of moment curvature MIDAS outputs. Can you describe generally your MIDAS model QC process and what other major things are you any other major things you are on the lookout for this project?
Oh, yeah. So um, it is a little tricky. We basically for QCing and Utah has a pretty rigorous QC process um, that a lot of other states um, don't don't have as much, and so Utah, you in the calculations, you yellow through everything. Um, Basically, in order to check the model, uh, the QCer often has to go into the model um, and look through everything. But we do have kind of go through the model tree um, and go through each of the elements in that. And also, um, as far as QC, we we do a lot of screenshots and a lot of output that we put into our count package to better to be able to have a thorough QC of of that process. Um, I also have like a I have some different spreadsheets or whatnot that have I can do some hand checks of that are more simplified than the minus model that I use to check against what it's giving me. If that answers the
Okay.
question.
Okay, and then the next one we have is which software was used for the 3D deliverable?
Um, the 3D deliverable software was a Bentley software, um, open bridge modeler, at least for the bridge, um, and that the all the utilities, all the other disciplines um, use Bentley, and it is it was easier to reference all the different elements in that way. But that was the software that we used.
Okay, we're almost done, I promise. Have you considered an elastic time history analysis? Um, why did you select the pushover analysis?
Um, we had not considered the time history analysis, and I think some of that was probably comfort with we had essentially we'd done a pushover analysis before, and um, I think we're more comfortable with that process um, and and the software and using that. And so that is mainly the reasoning for that.
Okay, the next question asks, with the seat width provided with the use of standard approach slabs and the anticipated longitudinal displacement, is there any concern of unseating of the approach slab during a seismic event?
Um, we uh, the approach slab seat is longer than. Actually, we use a pretty um, long approach slab seat, so it's longer than the anticipated deflection. Um, I wouldn't anticipate it unseating, but this was this was designed for life safety, so I think uh, we assume that there could be some um, misalignment of that approach slab, and that would still um, the bridge would still be able to to function to that level. But yeah, I wouldn't anticipate the approach slab unseating.
Okay, and then our final question for today says, what was the fundamental period of structure in longitudinal and transversal direction?
Oh, that is a good question. I I should have that up, but I think it was um, where was it? I showed that. Let's see. Um, oh, there we go. Yeah, it was between 1 and 1.5. I could probably provide that a more specific if I had, in a minute.
Okay. I think this concludes our session. Thank you, Logan, so much for this session. I know I could tell. I'm sure you could tell too. Everybody was really interested, very engaged as well. So thank you so much. I know everybody enjoyed it.
Thank you.
Have a great day, everybody.